Stationary energy storage is the largest and fastest growing deployment market for sodium ion batteries. Grid operators, solar and wind farm developers, and critical infrastructure managers are integrating sodium ion systems at gigawatt hour scale, not as pilot projects, but as long term infrastructure investments. The technical properties that define sodium ion's laboratory performance translate directly into commercial advantages at grid scale, and the deployment numbers reflect that alignment. Grid scale energy storage prioritizes three metrics above all others: levelized cost of storage, cycle life, and operational safety. Sodium ion's cost structure of $40 to $70 per kilowatt hour, cycle lives exceeding 10,000 to 20,000 cycles, and demonstrated abuse tolerance position it competitively against lithium iron phosphate across all three criteria simultaneously. Weight and volumetric energy density, sodium ion's primary performance liabilities in mobile applications carry no penalty in stationary installations. A grid storage container does not need to move. The physical size of the battery system is a secondary concern against a 20-year operational lifespan and a cost per cycle that undercuts lithium alternatives in high cycle applications. Sodium ion's reduced sensitivity to temperature variation provides an additional operational advantage. Lower thermal management requirements reduce the energy consumption and capital cost of heating, ventilation, and air conditioning systems within storage containers, a recurring operational expense in lithium-based grid installations that compounds over a multi-decade asset life. Stationary storage represents approximately 61% to 78% of total sodium ion demand across current market assessments. Deployments have moved from pilot scale to gigawatt-hour infrastructure contracts. CATL and HyperStrong executed a 60 gigawatt-hour sodium-ion supply agreement for stationary energy storage systems, the largest sodium-ion procurement contract on record at the time of signing, according to battery industry reporting. CATL's Naxtra battery energy storage system delivers 160 watt-hours per kilogram with a rated 15,000 cycle life, targeting utility-scale storage applications directly. BYD's MC Cube-SIB platform, built on sodium iron pyrophosphate blade cell architecture, specifies 10,000 plus cycles at a system voltage of 1,200 volts, with a designed operational life of 20 years or more. Lithium's Infinity Cell N162A system achieves 20,000 cycles at 94% round-trip efficiency, targeting grid stabilization and frequency regulation markets specifically. The Fulin Power Station in Guangxi, China, has released over 1.3 million kilowatt hours through sodium-ion grid regulation operations, providing a documented real-world performance benchmark for utility operators evaluating the technology. Sodium ion's integration into grid power electronics carries a documented technical liability. Unlike lithium iron phosphate, which maintains a near-flat discharge voltage curve through 90% of its cycle, sodium ion cells exhibit a sloping linear discharge curve. Voltage drops steadily as the cell discharges. Standard grid inverters are calibrated for flat discharge profiles. Applied to sodium ion systems without reconfiguration, they cut out early in the discharge cycle, potentially leaving 40% to 60% of usable state of charge inaccessible. Utility operators have characterized this as a credibility issue, arguing that sodium ion requires custom control algorithms and purpose-configured power electronics, rather than drop-in replacement of existing lithium infrastructure. Sodium ion's position in grid storage is commercially established and scaling rapidly. Its next frontier is mobility, where weight, volume, and cost intersect differently, and where a new class of affordable electric vehicles is being built around sodium chemistry.